This is the first video for Cat 6, nucleophilic addition and elimination. So basically what happens in this unit, or at least as part of this unit, is you are reacting carbonyl compounds that are not aldehydes or ketones with something else. And you're just changing you're basically changing the functional group that was initially there to something new. Okay, so you can't do it on aldehydes or ketones because the elimination portion requires a leaving group, okay? Carbons with negative charges and hydrogens with negative charges are not good leaving groups. So one example could be acid chloride, and there's a few other examples, but I'll just show this for now, okay? So basically the nucleophile attacks, this is the general mechanistic steps. The nucleophile attacks the carbonyl carbon, because this carbonyl carbon is a partial positive. Okay, it's an electrophilic carbon, and then those pi electrons go up to the oxygen. Okay, I can't tell if you can see that. Okay. And then, in the next step, those electrons come down, kick off what was initially there. And now you've replaced, so this is nucleophile, and you need nucleophile, and this is the chlorine. So now you've replaced what your chlorine was to now with a nucleophile. Okay? Basic mechanistic steps. So there's a stability ladder for this. And what that means is it's really easy to go from things that are on top of the ladder down, but it's hard to go from things that are on the bottom of the ladder up. Okay. So like with the last example, we had acid chloride. What that means is that it's really easy to start from an acid chloride and go to one of these things below it, but it's much harder to go from one of these things up to the acid chloride. Okay, and how they determine this is by looking at the stability of the leaving group. So the leaving group would be whatever was initially here and is replaced by something. So once that thing gets kicked off, like for example in the last step of the mechanistic step, the electrons and the oxygen come down and kick off what was initially there. How stable what was initially there is as a leaving group determines how reactive this is. So I see how that's inverted, but basically the leaving group, for example, on the bottom here, carboxylate. In order to have a nucleophile attack here, the electrons go up there and kick off this oxygen that already has a negative charge. It would now have a 2 negative charge, which is super unstable. So it's really difficult to kick off this oxygen and replace it with one of these things because you'll kick off something with a really bad, like really unstable charge, right? Whereas up here in the acid chloride, kicking off the chlorine is actually okay because chloride is pretty stable in solution. And then you can use this to infer the stability of acid halides, which you might need to know in your exam. So for example, an acid iodide would probably be more higher on the chain than acid chloride because I minus is more stable than Cl minus. Or at least that's in an aprotic solution. You probably won't have to worry about that. For you guys, I would just remember that acid iodide and then that means acid bromide are more reactive than acid chloride. Okay, so I'll leave that up there. Another percent. Okay, so then an example of two things that are of a similar energy, how would you do a reaction? So for example, this is called trans-esterification. So when you want to go from, let's say, a methyl ester to a ethyl ester, you have to add the nucleophile, which is your ethyl ester, and kick off the methyl ester, okay? So in this case, you can do this with basic conditions, like so. So ethanol and then ethoxide, sodium ethoxide here. So this is Na. And also on your exam, you're going to want to make sure that whatever your alcohol is, it's the same as your base. Because if this base is something else than the alcohol, then it's really the alcohol being deprotonated that'll be your nucleophile because that's your solvent, not whatever your base is. So for example, if I gave you add ethanol, this would be a fine to put for this reaction. Because this is not really your nucleophile, this is. Because this is in higher concentration than that. This is just a base that'll deprotonate your ethanol. Remember that the proton transfers happen first and they are solvent mediated. Okay, so then the mechanistic step for this would be just like what's shown before. Okay, you might ask yourself at this step, why do we kick off the methyl ester and not the ethyl ester? Or why do we kick off the methoxide and not the ethoxide? And the answer is that it can happen either way. It sure could have happened that on this first, after this attack, after the ethoxide attack, it went down and kicked off the ethoxide. That can happen. The idea is, though, if we have a super high concentration of the ethanol compared to the substrate, then our final product will have a lot more of the ethoxides of the ethyl esters than the methyl esters. So this is like back to like Le Chatelier's principle. If ethanol is a reactant here and methanol is a reactant there, then if we add a bunch, or let's say with the negative charge, doesn't matter though, is the reactant here, and methoxide is the reactant here, then increasing the concentration of this will push the reaction towards the product side. Okay, so this is all concentration based. So then we only draw the step that actually gets us to what we're going to have most in solution, even though, so I guess, you know, to show accuracy, these could be, so that could be 4, but this could totally be an equilibrium error. But you guys don't have to worry about that. So that could totally be a big equilibrium error, but don't worry about that. Okay, that's an example. A lot of these also can happen in acidic solutions too. I'll show that. Before I show that though, when making an ester, be sure not to use NaOH. Okay, so the reason why. So let's say you want to go from carboxylic acid with, let's say, NaO oxide. So the same conditions as last time. You will not get that. And the reason why is because the base will so this is carboxylic acid, right? Because this hydrogen is acidic. So the first thing that'll happen is that acidic proton will get deprotonated, and now we'll have a carboxylate. Okay, remember this was at the bottom of the ladder. Is it easy to go from something at the bottom of the ladder to something above the ladder? So a carboxylate to an ester would be going up the ladder. So you can't do that. So if you ever have a carboxylic acid and you want to change what's on there, you cannot do it in basic conditions. You have to probably do it in acidic conditions. Okay, the same goes for if you're doing a trans-esterification and you add NaOH, okay? So if you want to go from the same, let's say, methyl ester to ethyl ester, you cannot do NaOH and ethanol. So in this case, even if you had a much smaller concentration of NaOH, for every time that the NaOH or out of the water replaces this methoxide, it'll become a carboxylate and it'll be stuck there. Okay, so that's why I said earlier, whatever you want to replace it, so you want to replace it with ethoxide here, so like a ethyl ether, then you want to make sure that is also your base. So that's a K there to show that it's with a negative charge. Okay, so talking about the energy, because it's on the slide, so you might get test on it. So let's say if we're going from one ester to another ester, so we're using the same example of methyl ester to an ethyl ester. These are basically at the same energy, okay? But the intermediate step of once this thing gets added, it is going to be up here, so I'll show that. So once your ethoxide adds to the methyl ester, okay, the energy is higher. And the reason why is because we're breaking the resonance all around this carbon-carbon. So if I draw another resonance structure, so this resonance that exists here is no longer available here. So breaking resonance is destabilizing. So that also shows why reactions that are lower on the ladder, molecules that are lower on the ladder are difficult to go up. For example, if you started with carboxylate, the resonance here is really strong. Because this puts negative charge on both these oxygens, which is really stabilizing. So having a nucleophile come here and break that resonance is really destabilizing. So that's another reason why starting lower on the ladder is harder to go up.